So chapter 9 is on alkynes. So in order to get into this, you first need to know what an alkyne is, and you need to understand the structure. So recall that an alkyne is a compound with at least one carbon-carbon triple bond. And you'll recall that the carbons in the alkyne are both sp hybridized. They need to be in order to accommodate that linear shape. And I think that's all I really need to say about that. So it's something with a carbon-carbon triple bond. Oh, right. And recall that the triple bond will always contain, any triple bond will always contain one sigma bond and two pi bonds. So you need to know that as well. That's something you covered in Gen Chem. And there's no exceptions, by the way. Any triple bond between any two atoms will always have one sigma bond and two pi bonds. Always, no exceptions. Well, we already know something about carbon-carbon pi bonds, I hope, that we learned in chapters 6 through 8. We've learned carbon-carbon pi bonds react with electrophiles and undergo addition reactions. And so completely unsurprisingly, and I think we'll mostly talk about this on Wednesday after we get back, but completely unsurprisingly, a good number of the reactions that alkynes undergo are just like the reactions that alkenes undergo, except we use an excessive reagent and they happen twice. We use an excessive reagent and they happen twice with pretty much the same mechanism. And like I said, I think we'll mostly look at that on Wednesday. So what about naming alkynes? Well, I think if you can name alkenes, you can certainly name alkynes. You just use the ending YNE, ine, and best of all, we don't have any of this cis-trans or EZ stuff. That's off the table because the molecule's linear. There's no cis-trans distinctions here. But other than that, it's just like naming alkenes, only easier. In terms of, at least in terms of the structure of alkynes, I guess we've pretty much covered that already. Everyone okay so far? Just want to make sure I'm speaking English and making sense this Friday. But today I want to focus mainly on how it is that we make alkynes and just make sure that we understand how that's done and we understand the mechanisms, since there's no new mechanisms as far as that's concerned, as far as I can tell anyway. And then we'll at least start to get into the reactivity of alkynes and what are the kinds of reactions that they can undergo. So I've put up here a few abbreviations that I've been using, just and probably will plan to use today, but just to make sure we're on the same page. ET, of course, is ethyl group, CH3CH2, or you can write C2H5 if you want to use that instead of CH3CH2. Reason being that C2H5 is unambiguous. There's only one way to put together 2 carbons and 5 hydrogens. There is only one ethyl group. So that's one thing. And I think I've used the abbreviation PH for phenyl. That just means a monosubstituted benzene ring. You can also write C6H5 if you want to, perfectly acceptable. Because again, C6H5, everyone will know what you mean. There's really only one reasonable way to put all that together. Certainly the most common way by far is going to be a benzene ring. So please be aware that pH stands for a monosubstituted benzene ring. So if you wrote PHOH, that would be phenol, right? It would be a benzene ring with an OH group. If you wrote PHCH3, that'd be toluene. That'd be benzene with a methyl group. And we'll learn a lot of those common names of monosubstituted benzenes later on. The only caveat here is that if you have a benzene with more than one group substituting multiple hydrogens on the benzene ring, then you can't use pH. You have to draw it out. So pH is only and always used for a monosubstituted benzene. That is a benzene ring with exactly one hydrogen replaced with some other group. Although frankly, I've actually seen PHH for benzene. You can write that if you want to. But it's only and always used for C6H5. So any multiply substituted benzenes, you have to draw it out. At least that's how I've always been told to do it. That's my understanding. Good. So all that being said, what's the best way of making alkynes? Well, probably the most common way is by a double elimination or double dehydrohalogenation. So let's see. making alkynes by double dehydrohalogenation. And I think you can pick that word apart on your own, dehydrohalogenation, right? Loss of HX. And so, as it turns out, if you had, for instance, and we'll show in a moment that we actually know how to make this guy, if you had, for example, 1,2-dihalide, something like this, let's even put 2 phenyl groups on it, that would be a very good choice for making an alkyne from. And as I'm going to show you in a little while, we actually know how to make compounds like that already. So if you were to treat this compound with an excess of some base, we would need at least 2 equivalents of KOH or sodium hydroxide or sodium amide, something like that, that's a sufficiently strong base. You will get, actually in this case, diphenylacetylene. And the mechanism I think we know already. It goes by 2 successive elimination reactions. And we've seen, to some extent at least, elimination reactions already. We've used them to make alkenes. So if you've forgotten about elimination reactions, please review them. We talked about that at least briefly in chapter 8 in terms of how to make alkenes. And the very same idea is true here. So except we'll do it twice since we have 2 halogens available. And so from that we can make an alkyne. Good. So what would the mechanism look like? Whoops. KOH or sodium hydroxide or NaNH2. Probably with hydroxide, your solvent's going to be water. So what we'll do is we'll set up the molecule this way. Of course, our base is, in this case, hydroxide ion, though any sufficiently strong base would do. Of course, the potassium or sodium ion don't do anything. They're just a spectator ion. And so our base will pull off a proton, and always be sure that you're pulling off the proton on the carbon next to the one with the halide ion. These could, of course, be chlorides or iodides also, by the way. That would also work. So again, please be sure that you're pulling off the proton that's next to the carbon with the halide ion that you're going to lose. I think you'll see that we're removing this halide ion as a leaving group. And so I'm picking off the proton next door, not the proton on the same carbon. I think you'll find there's no good way to do this type of elimination that way. From this, we will get actually, this halogen will still be here. We'll now have a double bond here. And I'm going to show you another abbreviation, which is okay to put down, by the way, if you're in a situation like this. This wiggly line here means both cis and trans, or both E and Z. You'll get a mixture of E and Z. That's what that wiggly line means. You don't have to draw it if you don't want to, but it's perfectly good to put down like this. And we would indeed get a mixture of both, and it doesn't matter at all, because what's going to happen next, let me just make this look a little better, because what's going to happen next is the exact same thing. We'll have another hydroxide ion come in. That's why I said we needed an excess. And that will pull off this proton, again, the one that's on the carbon next to the halide that's going to leave. We'll push that in, get another pi bond, and lose another halide ion, and we will get our diphenylacetylene in this case. So there's no E or Z distinction with an alkyne. So it doesn't matter at all. So everything shown needs to be shown. Anything not shown doesn't have to be shown. I said I would try to stop talking like this. I guess I'm easing off little by little. But that's not that's not a new mechanism. Now the reason that I drew the squiggly line is because you would in fact get both during this reaction over here. You would get both this and this. depending on how the molecule was turned during the reaction. And the way you know that is because you're generating a double bond here. And remember, you can't rotate around a double bond. You can rotate around a single bond. You can't rotate around a double bond. So that's how I knew to put that, because these two are different molecules. One's E and one's Z. Let me do this correct. I guess this one would be the Z stereoisomer, and that one would be E, right? Because here the phenyl group and the bromine are on the same side, and here the phenyl group and the bromine are on opposite sides. So that's why I knew to do that, because those two compounds are different. Meanwhile, there's no squiggly line here, right? You can rotate around this carbon-carbon single bond between the BRs as much as you want. But once you form your double bond, it's got to be one of these two compounds. So that's why I wrote it like that. And it's okay to put that in a mechanism also, if it applies. Good. Does that make sense? So not that it matters, by the way, because as I said, in the end, there's no stereochemistry anyway. So so that's one real common way of making alkynes, is by a double dehydrohalogenation of a 1,2 dibromide of that type. And the thing is, we already know how to make a compound like that we learned in chapter 8. We learned that if you took, let us say, that compound happens to be called transstilbene, not that I really care if you know that, but it's a readily available compound. If you treat this compound with bromine in some inert solvent like chloroform, well then you will get that exact dihalide as a mixture of all possible stereoisomers. And I'm purposely going to leave it like that. I'm not going to go into what you do and do not have to show. I'm trying to encourage you guys to grow beyond that. The point here is that if we treat this alkene with, that's horrible, sorry, let me make that look a little better at least, with elemental bromine, we know that mechanism already. That mechanism actually is fair game for Monday's exam, if I recall correctly. So you will get this type of vicinal dihalide out of it. So we know how to make this. And what this means is we know in principle how to turn an alkene into an alkyne, where the triple bond goes exactly where the double bond of the alkene does. And that's something you will need to know. That's something that's going to be worth sticking in the back of your mind. Why? Because in chapter 9, later on in this chapter, we're going to cover organic synthesis, which is the idea of starting with some starting material and maybe doing 3-4 reactions in order to make a new compound at the end. And so this is one idea that you'll have down already. You'll know in principle how to convert an alkene to an alkyne, the corresponding alkyne. You simply convert the alkene to a dihalide, could be a dibromide or a dichloride. The dibromide isn't any better or righter or safer than the dichloride. They both are fine. And then you treat that dihalide with some base. So it'll just finish this idea. You'll treat that with either sodium or potassium hydroxide or some other strong base like that, and you will eventually get the alkyne. Yes, I'm sorry. This one over here I would say is called, she's asking what the name is. This one I would call diphenylacetylene, because remember, acetylene is ethyne. And this one happens to be called transstilbene, but I don't think I really care if you know that. Stilbene, S-T-I-L-B-E-N-E. Is that what you meant? Yep. Good. Can't really think of anything else as far as that goes. So, but that's an important step for us. We've learned how to go through 2 steps, really, you could almost call it 3, in order to convert an alkene to the corresponding alkyne. And you can do that from the 1,2 dibromide. And one thing that would be worth your time to take a look at, I'll leave it for you to work it out. In fact, you would get the same thing, though I'm not as clear on how to make this, but you would get the same thing from a geminal dihalide, meaning that the 2 halogens are on the same carbon. if you treated this also with an excess of KOH, or sodium hydroxide, or sodium amide, or something, you would also get the same compound. That would be something worth working out on your own. See if you can come up with a reasonable mechanism for that. If you want to bring it to office hours tomorrow and show me and see if you did it right, I'll be happy to take a look for you. But that would give you the same thing. Again, I'm not real clear on how to make that compound. Don't get me wrong. That would be real hard to make. But if you did have it, you could convert that kind of dihalide also into an alkyne. Good, so take a look at that in your own and see if you can come up with a reasonable mechanism for that. I promise you it will not be a waste of your time. That would be a good use of your time. Good, so, oh, one other thing I'll quickly add. This type of elimination reaction, we're going to have a lot more to say about in chapter 11. We're going to learn that this type of elimination, or this type of elimination, that's called an E2 elimination, or elimination bimolecular. And we'll get to that in chapter 11. So we'll revisit this idea then. We'll have a lot more to say about that. But even without that, I think it's a mechanism that we can make some sense of. Good. Yeah, I think that's all I need to say about that. Any other questions on eliminations by which we form alkynes, or the idea of going from an alkene to an alkyne? All right then. Let's clear all that out. Yeah, I'm getting typical Friday behavior. By the way, I don't think I've done this before. Something I've noticed over the years, this especially applies to Monday, Wednesday, Friday classes. Doesn't work for Tuesday, Thursday. But I wish you could all see what the class looks like by standing up in front. But Monday and Wednesday and Friday have completely different looks from the perspective of the front of the classroom. On Monday, I'm getting largely, you know, like I'm not exactly awake, which, trust me, I totally get it. I'm the same way. Wednesday is good. Wednesday, everyone's actually alert, and, you know, Friday is entirely different. On Friday, I'm getting, you know, like I'm up here, the action's up here. It's pretty funny. All of which I totally get. Trust me, I'm right there with you. I mean, I'm distracted too. As I said, I'm leaving town to go visit a buddy of mine tomorrow, or today, tomorrow, and Sunday morning. So I totally get it. Trust me, I'm right there with you. Good. Well, let's then, we have about 20 minutes left. I think that'll be plenty of time. Let's get into the idea of the reactivity of alkynes. And there are some reactions of alkynes that are special, which we'll have to get to next week, I expect mostly on Wednesday. But there are other reactions that we know already, that we have in our tool belt, so to speak, for alkenes in chapter 8. We understand the pi bonds in alkenes can undergo addition reactions with certain electrophiles, several of them in fact. And by and large, alkynes can do the exact same thing with the same mechanism, except that everything happens twice. So you need to use an excess of the reagent. So for example, I don't think anyone here, I'll put reactions of alkynes, or maybe reactions of alkynes part 1. But I don't think anyone will be surprised to learn that if you take an alkyne and you treat it with an excess, so you need at least 2 equivalents of some hydrogen halide, then you will get, oh, I might just have made a fool out of myself. Well, no, not exactly. Not exactly. I think we're fine. I would expect that you would get this type of dihalide, of geminal dihalide, where the 2 halogens that you're given are on the same carbon. It's going to follow Markovnikov's rule. And that's the only thing that's saving me from having made a fool out of myself. Because it looks an awful lot like what we had just a moment ago with the 2 phenyl groups over here. Trouble with that one is I'm not sure that we would get this compound cleanly. I think we'd get a mixture of 1,1 and 1,2 dihalides because the starting material is symmetrical. But, and we'll do an example of this and we'll show how Markovnikov's rule applies. Or I don't think anyone will be surprised that if you were to treat this with, of course, chlorine or bromine here, here it will be fine if the halogen is chlorine, bromine, or iodine. All that will be fine. But here we do need it to be chlorine or bromine. Fluorine's too reactive, iodine's not reactive enough. And we need some, inert solvent like chloroform or dichloromethane. And again, I don't think there's a soul here that will be surprised that you will get a compound with 4 halogen atoms in it, looking like this. The mechanism, again, is the same as before. We went over that mechanism in chapter 8. The first halogen adds, you get a 3-membered ring. You would still get a 3-membered ring here with a double bond in it. So that's really strained. That will then open up by halide ion attacking that and breaking open the ring, and then it will happen again. And the end result is you'll have this type of tetrahalide. Likewise with this reaction. Same mechanism, except it happens twice. The alkyne will react with the hydrogen halide, and you'll get at first a carbocation, then the halide ion will attack that. I think we'll go through an example of each of these. And then the same thing will happen again. You'll get a carbocation, and then the halide ion will attack, and you'll get a dihalide like this, where Markovnikov's rule applies. It's going to go through the most stable possible carbocation. So just to give some examples, let's say that we used, just to make sure, 1, 2, 3, 4, 5, 6, you can call that guy 1-hexyne, right? You remember how to name these. If we were to treat this with an excess of HBr, I could just as easily have used HCl or HI. I would expect our product would look like, let me get this right now. Yes. Oops. Let's not do nuclear chemistry. Let's keep them as bromines. I would expect we would get that compound. We'll do the mechanism in a moment. Actually, we'll do it right now. So how did I know that the bromines both went there? Well, because it's going to follow Markovnikov's rule, which you can say one of 2 ways. Remember, Markovnikov's rule says either the hydrogens will go to the less substituted carbon, and the other piece will go on the more substituted carbon. That's very true. It's just not as helpful. Or we could say the reaction's going to go always through the most stable of all possible carbocations. And I think you'll see it's an inevitable result that the halogens will wind up on that carbon. So let's see how that works. Let's react this with HBr. We need at least 2 equivalents. The first step is exactly what we learned in chapter 8. This carbon-carbon pi bond is going to swing away from the more substituted carbon and pick up a proton from your HCl, HBr, or HI. And you'll see that we will get the more substituted vinylic carbocation. So that will now be CH2. One of those 2 hydrogens was there to begin with. The other we just put on. And this is an okay structure. That's an allowable structure. It's a carbon with 3 bonds and no lone pairs. So if you work it out, it's a carbocation. It's just a vinylic carbocation. They're not real stable, but they are known intermediates in this type of reaction. So you need to know this type of structure is okay to draw, and that's going to be the intermediate here. Well, of course, now our bromide ion, it may or may not be the exact same one as from over here. In fact, I think it's pretty unlikely that it would be. But there are some bromide ions floating around, for sure, and one of them will come along and attack that carbon. And so I would expect that we would get that intermediate. Now, here's an idea. Why did I so confidently not worry about stereochemistry at all? I'm not doing any wiggly lines. Why am I so sure about that? Why did I know that it's okay to do that? Something worth thinking about. Yes, the negative charge on bromide is over here. So not chiral, not just not chiral. Well, you'll get both. No, there is no both. But this alkene has no cis and trans, right? That's a CH2. So there's no worrying about cis and trans. This is why I'm really pushing you guys hard with this. I don't want you memorizing rules for wiggly lines or wedge and dot bonds. I want you examining each structure you draw as you go and being confident about what you need to show and when there's something that you can show. Here there isn't. That double bond is neither cis nor trans, so there's no issue. Meanwhile, this will then happen again. Same mechanism that we learned before. And you will again get, the most stable possible carbocation, which will be this one here. This is now a CH3. It had been a CH2. Now it's a CH3 because it picked up another proton. And then your bromide ion. Let me do this a little better this time. There, now I think we're fine. That will attack our carbocation and we'll get our product. And again, I'm confident in not drawing wedges and dots. There's no chiral carbons here. This carbon has 2 bromines on it. Game over, not chiral. So that's what I want you guys to be doing. I don't want you memorizing rules and putting stuff down just to be safe. I want you thinking about the structures that you draw and having confidence about what you need to show and when you need to show it. Good. So, but do you all see what I mean? This is the exact same mechanism we had before, except it happens twice. And we could do the very same thing. Let me sort of move it over a little so I have a little more room. Let's use the same starting material. What if we treated this with an excess, meaning at least 2 equivalents of chlorine in chloroform? Well, I would expect that we would have a compound in the end that looks something like this, that you would add 4 chlorine atoms as a result. The mechanism is exactly what we said before, except it happens twice. Here's our chlorine molecule. Our pi bond swings out to form a bond to that chlorine, and then remember, the halogen atom also forms a bond to the other carbon in the, involved in the pi bond, and at the same time, we lose the chloride ion. So this is exactly the same mechanism that we learned in chapter 8, which, by the way, you'll need to know for the exam, but it's the exact same thing. And from this, we'll get a very strained species for sure. However, believe it or not, this type of intermediate has been experimentally determined. All these reactions have been very well studied. Our chloride ion will now attack at the more substituted carbon. Not that we can tell that because it's 2 chlorines, but it is known to attack at the more substituted carbon. And you will get oh, whoops. How about the octet rule? Octet rule is a good thing. I think you'll agree. And actually, here you would get a mixture of E and Z. Not that it matters, because in the end, you're not going to have any stereochemistry. This will then react with another molecule of chlorine, same exact mechanism. So you're going to form a bond to one of the 2 carbon atoms, and the pi bond is going to form a bond from the other, the other carbon atom in the pi bond. We will also break the weak chlorine-chlorine bond, and now our stereochemistry is gone. Whoops. wait a minute now. 1, 2, what am I missing? Why do I have only 3 bonds here? 1, 2, 3, 4. Oh, because the other chlorine is still there. Right, that makes sense. Yep, thank you. And so actually I think you'd get both stereoisomers there for the moment, but it's not going to matter. Chloride ion is going to attack over here at the more substituted carbon. So the mechanism again is exactly the same as what we learned for chapter 8. It's just that it happens twice. And now we have 2 chlorines over here, and this now is CHCl2. So again, no chiral carbons, no double bonds left, no issue of stereochemistry. Good, so that's how you would get that compound. But the thing that you need to know is that the mechanisms of the reactions of this type are going to be exactly the same as what you have to know from chapter 8, except we use an excess of reagent and it happens twice. So you can do reactions like this of alkynes very effectively. I would expect them to go with very high yield. Good. I think that's probably all I need to say about that. Any questions on hydrohalogenation and halogenation of alkynes? So that's one of the reasons that I do exams 3 and 4 are chapters 8 and 10 and then 9 and 11. Because my feeling is, depending how exam 3 goes, if you feel you need to redeem yourself on the addition reactions of alkenes, you'll get to do that in chapter 9, because all of that's going to apply. Oh yes, there are other reactions of alkynes that are special to alkynes that we'll also learn, but there's a great deal of overlap between chapters 8 and 9. And then the other reason, or there's probably other reasons besides, but another reason that I like to split up chapters 8 and 9 is, as I mentioned, chapter 9 covers organic synthesis and all those cans of worms that organic synthesis involves. I would rather postpone that to exam 4. I don't want you guys worrying about that also with the chapter 8 stuff. Let's postpone that to exam 4. And like I said, I think I have a few other reasons besides that, but that's basically my reasoning behind that. Good, well, we've got about 5 minutes left. So what I would like to do is at least introduce the idea of hydration of alkynes, which there is such a thing. Mechanisms are, in this case, maybe not identical to what we learned from chapter 8, but they're pretty similar. There's a twist, though, having to do with this ketoenol tautomerization, which we're going to touch on here. It's going to be something that you won't be responsible for the mechanism yet, but we will eventually get to it. And if I recall correctly, I think I will have a hopefully somewhat helpful reef session on that whole thing next week. Good, but I think, as I said, we have enough time to introduce the idea of hydration of alkynes, because they certainly can be hydrated, and there's reactions corresponding to hydroboration oxidation and oxymercuration. Now, your book says, and I'm not so sure that's my understanding, your book says that basically acid-catalyzed hydration of alkynes is not a thing. That is not my understanding, although I've never tried it. But I really thought you could do acid-catalyzed hydration of alkynes. And you would get, at first, an enol that would then, as we'll learn, tautomerize. But I will take them at their word. We'll assume that's not a thing. You certainly can hydroborate alkynes. And the reagents are the same. Borane THF, followed by alkaline hydrogen peroxide. Oh, actually, let me actually split this up so that we can see what it is we get. So from the first step, I would expect that we would get species that look kind of like this. Right? It's going to add the BH bond across the alkyne. And then it can do that 2 more times, of course, so that you have 3 of these vinylic groups attached to the boron. So all that is the same as with alkenes. So we get an intermediate that looks like this. And then, or it looks something like that anyway. And then if you add your aqueous alkaline hydrogen peroxide, you will get at first an intermediate that looks like this. You just put your CO bond with the OH group right where the carbon-boron bond is. And this type of structure is known as an enol. And the definition of an enol is in this picture. I'm using a structure or a picture as a definition. An enol is a compound that's an alkene with OH coming off of one of the alkene carbons. So you can use this picture to define the word enol. And as it turns out, these things are unstable. And they isomerize, or they undergo a special kind of isomerization called tautomerization, which we'll spell that word and define everything real thoroughly next week. But what you wind up getting out of it is a carbonyl compound. And that carbonyl compound looks like this. And actually I put a step-by-step method in your chapter 9 class notes for getting from this structure to this structure. And the steps go something like this. Step 1, turn the carbon-carbon double bond into a single bond. Step 2, change the carbon-oxygen single bond to a double bond. Of course, in so doing, you'll need to pull that proton off so that your oxygen has a charge of 0. And then you'll find another carbon next door that has only 6 electrons around it, so put the hydrogen there. I'll go over that again, but it's in the class notes. All of these steps, the step-by-step method is in the class notes. Step 1, turn the double bond into a single bond. Step 2, turn C single bond OH to C double bond O. Step 3, you'll find a carbon with only 6 electrons around it, make another bond to hydrogen there. That's in the class notes. Those exact 3 steps are in the class notes. And you're not responsible for the mechanism yet. We will eventually get there next term. But that type of isomerization is called a tautomerization, Tautomerization. And that word is also in the class notes with the correct spelling. So you're not responsible for enoketol tautomerization mechanism yet. We will eventually get there. And there's also, at this point I'm out of time, but there's also a corresponding oxymercuration reaction. This will wind up giving you the non-Markovnikov enol. So everything we said about hydroboration oxidation is still going to be true. There's not going to be any contradictions. And likewise, our oxymercuration equivalent that we'll cover on Wednesday will give us the Markovnikov result. So there's not going to be any contradictions with what we said in chapter 8 in terms of the stereochemistry of the outcome. But I am out of time. So I'd better call it quits for today. Any last questions before we do? Everyone's like, no, I want to leave. I get it, trust me. All right, well, have a great weekend. I will perhaps see you guys from Gainesville, Texas, I think it's called. That's where I'm meeting my friend tomorrow. Other than that, I'll see you all on Monday. Have a great weekend. Step 3. The steps of the step-by-step method are in the class notes. But basically, basically you'll find a carbon that is only 6 electrons around it, make a CH bond there. So it follows the octet rule. Good, see you all Monday.